This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 105. Hope your summer's going well. Today's presentation is on VIIRS and SAR Burn Scar Extent and Severity product. The author, Javier Villegas Bravo, goes our Satellite Liaison to the Ocean Prediction Center and Weather Prediction Center in College Park, Maryland. The discussion following the presentation will be facilitated by Jessica Cherry, the Regional Climate Services Director for Alaska. Just a few reminders before we get started. As you just heard, this session is being recorded. There will be an opportunity for Q&A after the presentation, and we particularly encourage attendees from forecast offices and regional headquarters to post their questions in the chat, and we will field them in the order they are asked. I'd also encourage attendees, if you haven't already, please identify your full name when asking a question, again, if you haven't signed in with your full name already. We are looking for future presenters. Please contact the VIIRS team if you are interested in presenting. We'd love to have you. And the training team can help create training materials that may be unavailable. Brian Mata at the Office of the Chief Learning Officer can handle your questions on that. I'd like to thank our VIIRS team, particularly Kashad Bowman, Lee Byerly, our Office of the Chief Learning Officer, the GOZAR, and the JPSS program, as well as our facilitator today. Without further ado, I'd like to introduce Javier Villegas Bravo as a faculty assistant at the Cooperative Institute for Satellite Earth System Studies, CISESS, as a satellite liaison to NOAA. His role is to enhance the use of satellite products and to develop new ones that will help Weather Service operations. Javier received his bachelor's in 2018 and master's in 2020 in atmospheric science from the University of Illinois at Urbana-Champaign, where he specialized in satellite remote sensing. Glad to have Javier back to the Satellite Book Club. I'm looking forward to your presentation. Take it away.
All right, thank you, Jordan. Yeah, so I was talking to the forecasters at WPC late last year, and I was shadowing them, and I was trying to identify new needs for research to operations, and one of them that I identified was burn scar, extent and severity, and I'll go ahead and just start the talk now. So I came up with this technique with VIIRS combined with SAR through a collaboration to show the extent and severity. Okay, so just a quick outline. So I'll go over some background, like what is a burn scar and like the problem we're trying to solve. Go over the product goals, what it's supposed to achieve. And then we'll go into the product itself. We'll do the physics with the passive imagery, look at a high resolution test case before moving on to VIIRS, which is a moderate resolution imager. And then we'll jump into the SAR problem, look at a test case, and then look at a situation where we can combine the two data sets. Then I'll go over the challenges that I'm facing right now in the project, future work, and a summary at the end. All right, so what is a burn scar? So burn scars result from wildfires, and basically when the vegetation burns down, it leaves a layer of ash and burnt topsoil. And what this does is it makes the ground, it destabilizes the ground and makes it more impermeable and hydrophobic. And basically, rain event X maybe didn't affect the area with concerning flash flooding, but now with the destabilized soil, this rain event will may cause some type of landslide, flash flooding, debris flow event. This map is from the United States Geological Survey. They do a emergency assessment of post-fire debris flow hazards, and basically this is the Dixie Fire from July 13th, 2021, and they have done a analysis outlining the burn scar extent, and in the shading they've shown the debris flow probabilities. And the way they came up with this is difference normalized burn ratio using Landsat, which is a high resolution passive imager, in situ observations to verify what Landsat saw, and a debris flow model, which is showing the probabilities shaded there. So one of the limitations is the fire is added to the map to like their website after the fire is done burning, so they can do the in situ obs. and so they can get all the cloud-free Landsat, smoke-free Landsat passes that they need. And it is not updated after, it is just stored. So that necessarily means that it's not capturing the aging of the burn scar, and during the burn scar event, during the wildfire event causing the burn scar, it's not capturing it. That's one of the limitations. So this is a mesoscale precipitation discussion from the Weather Prediction Center. One of the desks at the center is called the MetWatch desk, and they're in charge of 0 to 6 hour potential for flash flooding. And this is what the product looks like. There's a long discussion, kind of like a SBC convective outlook, if you will. And then they have a map, and the squiggly line outlines the flash flooding area. And the forecasters will underlay any relevant information to complement their discussion. So in here, this is a case from last May, I believe. And this is in New Mexico, and they've actually outlined burn scars inside their mesoscale precipitation discussion, which I assume was done using the USGS maps, because that's where I found out about the USGS maps on the shadowing the MetWatch desk. So you can see these broad areas, and actually when I look at the satellite imagery, the burn scars are much smaller, surrounded by areas of desert and vegetation, and I think we can enhance this. Maybe we can even overlay a burn scar product in the mesoscale precipitation discussion directly by having it available in AWIPS, for example. So here in the discussion, we say these model hourly rain rates that they're getting between 0.5 and 1 inch over the burn scars across New Mexico and Colorado. With this rain rate, about 1.5 inch in 1 hour could lead to quick runoff and flash flooding. So some backgrounds on the burn scar problem, just to outline it explicitly. So we need a way to rapidly and continuously monitor burn scar extent and severity. So as the fire is happening right after, but then also like as it ages. So this will assist with the flash flood advisories when rain events are occurring. And yeah, like I said, the burn scars age with time and become less prone to flooding. The vegetation will grow back, the soil, topsoil will run off, and you'll get the old soil back, and so on. So there are high resolution imagery from Landsat and Sentinel-2, which is considered like the gold standard because they can see the fine details in the perimeter and the severity, but the revisit times due to the swath widths are very, very low. I think it's 5 to 6 days, maybe in the constellation a little less, and then there's the issue of like smoke clearing and cloud clearing the data. And then passive imagery itself has the problem that it can't see through clouds or smoke or at nighttime. So if there's a nighttime fire, nighttime rain event, it would be nice to see that as soon as possible. So solutions. So you can use moderate resolution imagers like VIIRS or MODIS. They have daily global coverage, and you can basically aggregate the latest cloud-free pixels over maybe an 8-day period, for example. And then to get past like when there's just cloud over a long period of time or smoke or it's nighttime, we can fuse it with an active technique using synthetic aperture radar like Sentinel-1 or RadarSat, which there are many of, and there are many imagers as well. So you could even make a faster time series, but I think daily is mostly good enough. So the product goals, successfully assist the Weather Prediction Center with their mesoscale precipitation product, the 1 0 to 6 hour potential of flash flooding, and even potentially with their excessive rainfall outlooks. So when they do their excessive rainfall outlooks, they're looking at maps to see like climatologically what kind of rain rates, what rain amounts are going to cause flooding. And new burn scars and even old burn scars will kind of change that climatological number, right? It'll make the area more sensitive. I want it in AWIPS too, so they can overlay it and put out their products with the burn scar mask in it. So it'll be a daily updating, 8 to 16 day running cloud-free composite. Later I'll show an 8-day composite. It can be cloud-free during the summertime, but you know, there's other times maybe in the winter or just it's particularly cloudy time of year where I may increase this. Yeah, so VIIRS has daily global coverage at 750 meter nadir resolution in the bands that we need. And I want the composite to only show the burned area. And the reason is, so there are RGBs to see burn scars, like the daylight and cloud fire RGB. but it shows everything, not just the burn scars. So it's a lot of noise with like desert, and basically the perimeter, the transition zone from burn scar to not burn scar, there's like some uncertainty. So it's just a lot of noise. It'll have better performance in AWIPS too if we just show the relevant parts of the data, and it'll be a less cumbersome overlay. So it'll be easier to see all your model data and other satellite data that you want to look at. And the last thing is to combine it with SAR for the cloud, smoke, and nighttime support to complement the VIIRS imagery, which I'll show in a bit that I use solar reflective bands. So, and then the next slide. Okay, there we go. Drink water. Yeah, so the two bands that we're using are the veggie band, 0.86 micron bidirectional reflectance factor, and the 2.25 micron BRF. And then the reason we're using BRF, it's a solar zenith corrected reflectance value. So it's just normalized for the sun angle. And basically using these two bands, the vegetation is much more reflective than the burned area at the veggie band, and at 2.25, the microphysics band, the burned areas are much more reflective than vegetation. So they have opposite signatures, and you can kind of create a version of NDVI, which is called normalized burn ratio here. And classically, normalized burn ratio is used in a differencing technique where you take the post-fire MBR and the pre-fire MBR and subtract them. And a positive would indicate higher severity, down to 0 was a low severity burn, and then negative would indicate that the area is like regaining vegetation. But it does have some limitations, like season to season, you know, it goes from summer to winter and the ground becomes like more bare soil and dead vegetation. So the MBR will increase, but there isn't actually like a burn scar there. So I believe this would require some kind of tracking and like decision making on what the pre-fire normalized burn ratio area should be and what the post-fire one should be. So here in the top left corner, well, just overall, I've taken a NOAA 20 VIIRS granule from October 14th, 2021, and this is located over Northwest California and the Oregon area. Here's the Dixie Fire from USGS that I showed earlier. And here's a normalized burn ratio over the whole swath. Here's the veggie band over the whole swath. And here's pretty much just a burn scar mass that I came up with. And essentially what's going on is that I use the 0.86 band to do the extent and the perimeter of the burn scar mask. I've also used the 2.25 micron to help with the perimeter, and I Gaussian blurred them with an area where the rest of the area is zeros after I threshold the image. And what that's done is it's created like a nice coherent boundary around the burn scar. And what I've overlaid in the valid area is just the normalized burn ratio. So this is just like a clean way to look at the burn scars. So here's the dayline cloudfire RGB again. You can see the 2.25 micron and the 0.86 micron. So 2.25 is red, so the burn scars show up as red. They're really reflective. 0.86, the vegetation is really reflective, and the burn scars are really dark. So you can see the burn scars are red, the rest is green, and then the desert has a lot of reflectance in this red band, which is in the blue channel. So you see like this bluish, brownish color for the desert. And then what I've done is I've taken my burn scar mask and I've just overlaid it. You can see what's going on. There's a little bit of noise, but it generally does a pretty good job. You can see all these red areas right here from fires up here, sorry, around here. Yeah, so it's not perfect. It's not a science quality data set, but I do think it would be very, very good to have an AWIPS too for the forecasters. And basically how I imagine this used, maybe you have some field like QPF or like a radar or some storm going over or some other model fields, whatever the forecaster would want. And then they can see, okay, look, I have my setup here and my climatology says this, but look, I got the burn scars overlaid, and this one, for example, is fresh. This one's just from this year, so I can say, I can like using forecaster experience, I can say, okay, well, it'll flood maybe with a little bit less rain this time around. So kind of how I arrived at those thresholds, I coded this up in Python. I basically took the RGB, I split it up into its components, 2.25, 0.86, and 0.67, and then I made a histogram of each one. And I coded up these sliders to like threshold them in real time and see which part of the histograms correspond to like the what in the image. So the veggie band, I was able to grab the burn scar areas, the extent really, really well. You can take out the water, but it does also grab the water over here. And then for the 0.6 micron band, it doesn't really show much, just the desert's highly reflective, so not too informative. 2.25 micron kind of correlated, but it does, but in other examples like the RGB, we do see that it's like firing higher for the burn scar areas. So I see a labeled part of the histogram myself, just like desert and vegetation is bright in the veggie band. So maybe this peak is vegetation, and then over here is like desert. And then 0.67 microns, so maybe this little hump is desert, and so on. So you can kind of go through those exercises. That's how I came up with the thresholds by hand for this first round. Then I decided to dive a little bit further into the statistical analysis. So I wanted to see if I could like use some sort of clustering technique to find the burn scars, and like the short answer is no. So basically I have NDVI and NBR, 0.86 microns versus NBR, and 2.25 micron versus NBR, and 0.86 versus 2.25 micron. So there are clusters that show up really nicely, but most of them actually match up with desert and vegetation. That's the majority. But I wanted to see, okay, so like if I take all of this data and I get these clusters, what if I just take a burn scar amount? Like, do I get like some nicely clustered data? So I just zoomed in on one of the burn scars, and then it leads to this histogram, and I can see some relationships forming in these histograms. And okay, so like what am I gonna? So I want to compare it to the total area. So I have this, and then that I sampled from here, and then I have this whole image that I made the histograms for, the 2D histograms. So I found that these signals from the burn scar are actually happening in the tails of these histograms. So I was thinking, you know, initially an unsupervised algorithm, some sort of clustering Gaussian mixture models, for example, to find the burn scars. But I think it's going to be more complicated. I think it's going to have to be some sort of like, I still have to label the data, so I still have to grab like a chunk and do these histograms approach. So just looking for a generalized way to do the thresholding or find them in the future for problems I'll explain in just a second. So just to show how powerful the 2.25 micron band is, I want to show this high resolution Sentinel-2 case. So this is from the multispectral imager. I got these images off the Sentinel playground, and this one's from June 2021. This is before the Dixie fire, and this is the Dayland Cloud Fire RGB. Here's the color. And basically you can see like these dark greens here in the color image, and the greens are really bright before the fire. This next image is in September, so a few months later, and the fire is mostly burned. It's got some active burns up here and over here, and you can see in the color image like the ground has darkened, and you can see this vegetation going towards not vegetated anymore. And then just this image is just from this past June, and I thought it was really interesting to see how the burn scar aged. So you can see these dark bright reds over here, and then less than a year later, they've lightened up quite a bit, maybe some vegetation regrowth on the edges, and even the soil and the color imagery has changed color, going from this burnt to this red soil. So I was like, all right, let's make my own composites. Let's make a cloud-free composite of the VIIRS Dayland Cloudfire RGB, and I can use the same bands in the RGB to make the burn scar mask. So there's some noise, there's some issues like with the bow tie deletion and the reprojection that I'm still working on, but I basically eliminated clouds in the image. I downloaded the VIIRS data from NOAA 20 over the Western CONUS for the 2021 fire season. It's kind of June through August. That's how much would fit on my computer. So right now, so I limited to that. This is 8-day composite, and I saw pretty good cloud-free coverage. This is later in August 12th through August 21st. You can see there's a lot of smoke piling up due to the fires in the composite. I haven't decided if I should delete the smoke, but definitely like the SAR will help a lot in these situations. And then here's just the next 8-day composite. So you can see from July 10th through 18th, there's no fire, no burn scar right here in the Dixie area. And then after compositing after August, it's kind of like finished, it's kind of still burning and going, and it's kind of finished and kind of appears. So I just zoomed in and I added the burn scar mask to the composite. So before I showed you a single granule with hand-chosen thresholds. This is the same thresholds, but over my composited granule. So what I saw is the thresholds definitely need some smoke tuning, although the SAR may help with that, but some sort of smoke detection to not have the mask valid. Different viewing and solar zenith angles. When you combine all the granules, you're basically like, you can see some bow tie deletion here, and like you stack them together, like somewhere at some observations at the edge of the swath, somewhere in the middle. The swath may be from like towards the side, so it comes in at a different time of day, that particular swath, so the sun angle is different and all these things, and that will affect the scattering based on the sun view geometry of the satellite. And then that'll in turn affect the thresholds that we need to use. But basically you can see it's got pretty good behavior. It's capturing the major burn scars and even some smaller minor ones over here. And at the very least, it grabs the attention of the forecaster, and I think it's within the precision that they would draw their flash flood advisories at. All right, so physics of the problem for the SAR imagery. So I adapted this slide from Dr. Roger Michaelides. He is, I think he just started a professorship at Washington University in St. Louis. He was at Colorado School of Mines before, where he developed this interferometric SAR technique from Sentinel-1, and basically it just looks at the distance change in the line of sight of the SAR between a pre-fire and a post-fire image. I believe I'm getting that right. And basically they can detect surface deformation. So here's like an example of what that looks like. And the idea is that the surface deformation is correlated to the surface deformation caused by a wildfire. And you can therefore see the burn scar and potentially see the burn scar severity, which he claims that it is able to do. So here's an example from the interferometric technique on the left, and then he has a Landsat image. This is a fire in Colorado, and you can basically show it has pretty good matchup, and it can see through the clouds, which is really awesome. And later, after the fire is like done burning, he produces soil burn severity map, which is really cool. And basically, I found the fire in my like composited VIIRS database that I made. You can see the bow tie deletion artifacts here, but anyway, here's a dayline cloud fire RGB. There's like clouds in the way, so I imagine like taking this SAR image and like overlaying it here for support, and then normalized burn ratio. Here you can see how the clouds affect the 2.25 micron band, and these clouds are optically thick cumulus, so we're not really getting any contribution of radiance from the surface at all anyway. And here's just the cloud mask showing what's going on. So challenges, the thresholds aren't valid. The ones that I made aren't valid from granule to granule due to sensor zenith angles and general sun view geometry and smoke. Combining high resolution SAR data with low resolution imagery in a viewable way. So like, I think the SAR imagery is like 50, 100 meter or something like that. And the VIIRS imagery is 750 meter at nadir. So it's a challenge combining that. I think geotiffs may just solve that problem right away. And one of the challenges is the importance of the burn scar severity signal to the flooding sensitivity in the forecast scenario. So when I showed the mesoscale precipitation discussion, it just said burn scar. And it used the USGS map, which showed kind of like what's going on. But I want to understand that more, especially with respect to normalized burn ratio. Future work, I want to combine the SAR imagery with the passive imagery automatically and have like nice animations of that. And then just the same thing I said, just have all the overlays together for the 2021 fire season and show that it works and that it's enjoyable to use and that it looks good. And I want to match it up with a case where flood risk was issued by WPC. So get a nice case where like all the parts of the composite are being used. And a summary, so just a couple things. So I'm presenting this this work at the AMS Collective Madison meeting on Tuesday, August 9th at 2:15 p.m. Central. It's the fire session in the JPSS part of the conference. And I hope to have a lot of that future work done by then. I'm really interested in feedback from the experts to shape this project. My background, my master's thesis was on cloud detection, and it's actually a really similar process. I reused a lot of code for reprojecting the data, grabbing the data, analyzing the data. It was really interesting actually, but I'm not a subject matter expert on burn scars and I want to become one. So any feedback is appreciated. My email is down here. But anyway, the summary, we created a way to get burn scar extent around a coherent area without much noise. So that was like that, where we thresholded 0.86 and 2.25 micron BRF and then Gaussian blurred the perimeter. And then we like inlaid the normalized burn ratio where that perimeter was valid. We created a cloud-free daily updating composite. So I basically was just able to show that I can grab all the data, composite it together, make a cloud-free scene that can update daily, and I can overlay the burn scar mask on it. And we used MBR and 2.25 micron BRF as a proxy for severity. It may not be as good as difference normalized burn ratio, but I think it should get the job done. But I'm interested on feedback. I like that it doesn't use image differencing because I think it's really simple that way. And it can just, everything is automatic. And yeah, thanks to Dr. Roger Michaelides. They're creating the INSAR component and collaborating with me to provide cloud, smoke, and nighttime support. And yeah, thank you everyone, and I can take any questions now.
Super, Javier. This is Jesse, and I encourage everyone to stick around here for a couple minutes for a discussion. Great talk. Yeah, maybe I'll get us started on a couple discussion questions, and then we'll take some from the audience. So I encourage audience members who want to throw a question in the chat. We've got one already, so go ahead and think of a question, put it in the chat, and I'll get us started. So Javier, I do think that this is an important field of research, and that there's growing awareness of the risk of these post-fire debris flows, and that is a interesting, impactful field of work, especially now that the severity of the fire season seems to be increasing in some places. I know up here in Alaska, we have already a very severe fire season this year. So a couple questions. In terms, and I realize you might not be an expert in the debris flow model, but I wonder if there are parts of the model that might have other data sets that could be brought in. So for example, does the age of the burn scar matter for kind of the threat of debris flow?
Yeah, I think it does. And I talked to some forecasters and they think as well. So after there's like all the ash and burnt bits and debris on the ground, after some time it'll like get washed away and disappear and blow away, and the soil starts to recover and the vegetation starts to regrow. So that will like serve to stabilize the soil again. So after you run your debris flow model once, it'll be valid after the fire, but then like it'll like the burn scar will maybe last 6 months to several years, and then the flash flood sensitivity will wane down quite a bit.
That is what I would imagine. And I would guess in some ecosystems, you have very slow growing topography and others may have, vegetation that recovers much faster. So that might be an interesting thing to kind of layer in for forecaster awareness at some point. Yeah, and I wonder if your technique could also be used to actually detect that revegetation and recovery process.
Yeah, definitely. That might require some differencing, but it can do it.
Okay, cool. Well, it looks like a few questions have come in here. So why don't I ask, Bill Schoberg wondered, how long does it take you to create the product after a fire event?
Yeah, so the code is pretty bare bones. It's just a couple of thresholds and then like this like SciPy function to do the blurring, and then calculate the normalized burn ratio, and then create the composite. All in all, it's like a few minutes, no more than that, plus the latency of the VIIRS data. So I don't know how long it takes the receivers, or maybe like in Alaska, right? And maybe like every hour and a half you get the orbit or something like that. So that would be the latency.
Okay. But including the SAR.
Oh yes, the SAR component. I do not know the answer to that. That also uses a thresholding scheme. I would have to ask Roger about that.
Okay. A question came in from Bill Line, NWS, or a comment. NWS offices have access to detailed burn perimeter maps pretty quickly, sometimes during the fire from aircraft IR, and eventually burn severity from bark and bear maps during or quickly after the fire is contained. The advantage from VIIRS would be that the burn severity information would be available quickly during the fire. And apparently Sam Batsley from SIMS is developing a tool that does this. So he suggests that you might talk with Sam.
Yeah, so actually I am collaborating with Sam. So he's doing like some NDVI work, and I wasn't aware of the aircraft situations. But yeah, no, definitely I'm talking to him, and he's been giving me feedback. And actually, he offered to, when the product is ready, to test it out in the Real Earth web viewer. So I hope to make the product public when it's ready, and it'll be a complement to his work. I don't think he was focusing on NDVI more over the burn ratio, as I recall.
Okay. And as the follow-up to that, it might be, do you have collaborators on the USGS side as well?
Actually, I don't, but I would love to, because yeah, I mean, they kind of inspired this whole thing, actually.
Yeah, that might be good. Question here from Jordan. He says he might have missed this, but has normalized burn ratio previously correlated with flood or debris flow severity, or are there other factors, terrain, temperature, et cetera, that must be considered?
Yeah, so actually, I forget what the data source is from, but our forecasters in AOS also have like the stream flow maps that kind of outline terrain and topography to assist in that. So it would be like a combination, you're right, of like what the burn ratio is, but also like the local topography mixed in with like climatological values of like rain rates that cause flooding, like an inch in an hour, 5 inches in an hour, something like that.
Yeah, and I remember from my time at the River Forecast Center here in Alaska that a lot of those are kind of rules of thumb that in terms of rain rates and anticipating potential events, and those aren't necessarily coded into AWIPS. You just sort of have to know them, or they're on, you know, a Google sheet or a sticky note somewhere or whatever.
Yeah.
So yeah. I always thought it might be good to have more information about infrastructure in AWIPS. Again, that's something that there's like major roads and things in there you can look at, but that might be helpful for forecasters as well.
Yeah, definitely.
It looks like Lee's chiming in. Andrea Lloyd from USGS, the AROS Landsat program, she's going to be presenting here at the Satellite Book Club on July 21st on Landsat products for post-event analysis. So that's cool. That'll give folks a chance to come back and talk again more about burn severity.
Yeah.
Brent Bauer says it would be nice to get these VIIRS maps correlated to burn severity maps that have some ground evaluation for comparison. One of the issues with burn scar flash flooding and debris flows is that not much, if anything, is done to evaluate the burn scars afterward in the intervening years. So how to age out the burn scar effect. Having a continuous monitoring from satellite would be very valuable in evaluating that. Yeah, would you know anything about that, Javier? Or that might be another reason to collaborate with USGS, who might be doing more ground-based work.
Yeah, so basically, I think with the age of a burn scar, there's a couple of ways to do it, but what you can do is you can do a running time series of the difference normalized burn ratio. So basically you can see how it's aging relative to itself. You can also maybe like normalize like the max MBR and like in between the max and the zero, in between 0 and 1, and then use it as like an index of how strong it is, and then over time a forecaster would notice that maybe weakening. And then as for the ground truth as it ages, the high resolution imagery as a qualitative source looks very, very valuable. So we saw in the color imagery that the soil changed colors from like black to like a reddish brown as it aged over a year. And we saw it turn from like basically like green vegetated to black as it burned. So I think just looking at the color imagery will be really important too, just a visual. It's like 10-meter imagery, which is insane.
Yeah, amazing. Well, I think we have one more question, then I'll make a couple announcements here. But Dimitri wants to know what kind of resources you use to learn to use Python for the satellite image processing.
Yeah, so I guess the long and the short of it is I did my master's thesis in satellite remote sensing. So I just kind of, my postdoc in my group, he showed me how to like order the data and open up the data in Python. And then as for learning how to use Python, I mostly use matplotlib for my visualizations, NumPy and SciPy for any type of number crunching. And then there's a slew of like georeferencing and reprojecting libraries that hurt my head and make me very angry. But it's kind of just years of experience, and this was really difficult. I was staying up until like 2 a.m. for several nights leading up to this talk, just trying to make the figures and make the composites and make the databases. Use like 200 gigabytes of my hard drive, and I have to let code run overnight and stuff like that. So it's a labor of love. You have to really like the process and just Google everything. Yeah.
Good advice. Well, excellent, Javier. This was very interesting. And I think that it seems like a lot of potential here for improving awareness about the potential for these events. A couple of announcements. In the chat, Lee has posted a survey. If you want to provide feedback on this Satellite Book Club event, next week we're going to have a talk from Chad Gravel at the same time here from Southern Region Headquarters. Also work with Ted Ryan from WFO Fort Worth and Stephen Zubrick from WFO Sterling and John Centennial from SIMS. They're going to talk about the Prob Severe Lightning Cast product. And then it sounds like we're going to circle back on fire again later this month. If you do have questions or want help with configuration of satellite products, we've got some information on the screen here. Kashad Bowman on the TowerS team for any comments or questions about the book club. Tons of resources. This is a really valuable community. I encourage everyone to contact the community and each other and learn more, and we'll get more and more from these satellite products. Anything else I forgot to mention here from Jordan or Kashad?
Well, Jesse, I think I can take it from here. I think you covered all the major announcements, so I really appreciate you facilitating today. And Javier, thank you so much for your presentation. In fact, I'm looking forward to hearing this presentation at the AMS Satellite Conference Collective Madison meeting coming up here in a month. And I regret a little bit that you were staying up so late getting these figures put together, but this was a great presentation and really in the spirit of the Satellite Book Club to discuss new and innovative satellite applications that have some applications to the field. So really appreciate it. Really appreciate all of you joining us today. And again, I hope you join us next week. Until then, thanks a lot and take care.